Hello, welcome again. We are covering the subject thermodynamics for civil services means IFS and various gate exams, and we have started the chapter first law of thermodynamics applied to flow processes. And in this we have covered the topic steady flow process, and there are some examples of steady flow process that we will cover in this video. First example of application of steady flow process is nozzle and diffuser. So first of all, what is nozzle? Nozzle is a device in which velocity is increased at the expense of pressure flow, and diffuser is a device reverse of nozzle, means pressure is increased at the expense of penetrator. Okay. So these are opposed. Nozzle increases velocity, it decreases velocity. Nozzle decreases pressure, it increases pressure. Okay. So this is your typical nozzle. This is your inlet condition. This is outlet condition. As we are discussing steady flow process, so mass flow rate is same. So here mass everything is same as that the mass rate. And the steady flow energy equation is this that we have tried. So in this case, or in the case of nozzle, we can see that no external heat is supplied. That means dq by dm is 0, and nozzle itself does not do any work. So it means dwx by dm is 0. Both inlet and outlet are at same level, then z1 is equal to z2. So now this equation will reduce to h1 plus v1 square by 2 plus h2, sorry, is equal to h2 plus v2 square by 2. So this is equation number 1. And for mass, this is energy balance per unit mass, and for mass balance a1 b1 by specific volume, that is your volume flow rate versus specific volume mass flow rate at the inlet, and this is at the outlet. So inlet and outlet mass is same, mass flow rate is same. Okay, so this is continuity equation, this is with energy equation. So if at the inlet the velocity is very small compared to outlet velocity, so we can take v1 equal to 0, so v2 will find out. Okay, so v2 will be your root 2 h1 minus h2 within bracket. If h1 minus h2 in joule per kilogram, then v2 will be in meter per second. Okay, so now this is the case of nozzle. In case of diffuser, this v2 will be less than v1. Okay, or we can say if v2 is very small as compared to v1, so we will find out v1 as h2 minus h1 into 2. Okay. So this is in case of diffuser. Okay, so I am just reading out this. A nozzle is a device which increases the velocity or Ke of a fluid at the expense of its pressure drop, whereas diffuser increases the pressure of a fluid at the expense of its penetrance. This figure shows a nozzle which is insulated. The steady flow energy equation of the control surface gives. So this is your steady flow energy equation. Okay, and this equation reduces to this when we apply heat transfer 0, work done 0 per unit mass, and z1 is equal to z2. And the continuity equation is w a1 v1 by small v1 is equal to a2 v2 by small v2 for steady flow. And the inlet velocity is very small compared to exit velocity v2. The equation becomes h1 is equal to h2 plus v2 square by 2, or v2 is the constant, where v2 will be in meter per second if h1 minus h2 is joule per joule. Okay. So this equation 1 and 2 also hold for diffuser. In this we can neglect this and find out v1, whereas in nozzle we are found out v2. So this is the nozzle and diffuser application of steady flow process.